Okay, let's now look at the differential equation defined by the system of equations defined by the matrix we see here, 3, -2, 2, 7. Again, assuming this is the matrix and the equation y prime equals ay, we assume a solution y equals e to the lambda t times x1, x2. We obtain the two simultaneous equations we get from this equation, setting, well, this equation, this familiar step, and also the determinant of this matrix being equal to 0 gives us three equations and three unknowns. The determinant of the matrix is lambda squared minus 10 lambda plus 25, easily seen. If we multiply the diagonal elements, we get lambda squared, we got a -7. Well, we got a 7 and a 3, which gives us 10. Both being of the sign opposite, the lambda, that gives us -10 lambda. And we get plus 21, which added to the negative of the product here, which is -4, so the negative being plus 4, 21 and 4 gives us 25. We get this. This is easily factored, giving us repeated solution. Lambda 1 equals 5, lambda 2 equals 5. Had we plugged into the quadratic formula, we would have gotten 5 plus or minus the square root of 0. Again, the plus and the minus both giving us solution 5, so we again get a repeated root, lambda 1 and lambda 2 both being equal to 5. So lambda 1 equals 5 gives us this equation, again simply substituting 5 into this. 3 minus 5 is -2, 7 minus 5 is 2, gives us this equation, which gives us two equations, each giving us the same result, that x2 has to equal -x1, resulting in the eigenpair 5, 1, -1. And the solution y1 equals e to the 5t times the column vector 1, -1. Now, what do we do with lambda 2 equals 5? We can't just repeat what we did. We would end up maybe not with the identical solution, but we would have to end up with a solution where we have e to the 5t and a vector here where these two numbers are equal and opposite. And that would be a multiple of this solution. So that doesn't lead us anywhere. Now, having a repeated solution, if you recall in the preceding chapter, with second order equation of a single function, second order linear equations involving single functions, if we had a repeated root, we would multiply our first solution by t and obtain a second linearly independent solution. Now, we can't exactly do that here. If we just multiplied this vector by t, we would still end up with the same eigenvector here, and we'd have a problem there, and there would be other problems with that. So what could we do? We could try a solution of the form y2 equals e to the 5t times v, where v is an unknown function of t, and solve for that v. But if we try that out, we see pretty quickly that it doesn't work. Without going into detail, same thing happens if we try a multiple, t times e to the 5t times some unknown vector. That doesn't work either. However, if we try sort of a combination of these two approaches, letting y2 equal t e to the 5t times one unknown vector function plus e to the 5t times a second unknown vector function, it turns out that we're going to be able to solve for these two vector functions and obtain a second linearly independent solution, which combined with our first will give us a fundamental set solving this equation. So let's see how that works out. First of all, this function will hopefully be a solution. We want y2 prime to equal our A matrix times y2. And we furthermore want that to equal our eigenvalue, which is 5 times y2. So keeping in mind that this is our goal, let's just start by taking the derivative of y2. We get y2 prime equals the derivative of t e to the 5t is, I'm just going to assert this, I wave my hands and explain it, but that's going to be e to the 5t times 1 plus 5t times our unknown v1 function, and then plus 5e to the 5t times v2. And the derivative of t e to the 5t, just by the product rule, is e to the 5t from the derivative of t, and then from the derivative of e to the 5t we get 5e to the 5t, and that's going to be multiplied by t. That's where we get the 1 and the 5t. If you simply write it out, you should easily be able to verify that step. Now, without getting our hands too dirty here, we can see that ay2 should equal 5y2. And without getting our hands dirty and writing out the coefficients of a just yet, that tells us that a multiplied by the matrix, the column vector, t e to the 5t v1 plus e to the 5t v2 should equal what? 5 times y2. So that should be 5t e to the 5t v1 plus 5e to the 5t v2. This equality, along with the condition that this should also be equal to the derivative y2 prime, will allow us to determine the vectors v1 and v2. And we'll go on with that in the next clip.